Hi, so I'm making a video on something I've been studying lately, which part of it is Einstein-Cartan theory, which I think is sort of a generalization of general relativity, or perhaps a alternative. So this says, what are the pros and cons of Einstein-Cartan theory as an alternative to GR? I hear that it can avoid the initial Big Bang singularity, as well as singularities in black holes. So why does it appear to be talked about so little? So my reason or motivation is that, general relativity, as I understand it, doesn't really involve twisting. Now there is something called a Kerr metric, which does have a rotation. But I think that is about rotating coordinate systems. I'm not sure that... I think this has other things to offer that are different from the Kerr metric, and I'm interested in that sort of thing for complicated reasons. But, and actually I've been studying a lot of Cartan's. So Cartan is this mathematician. Let's see, Cartan, who is here. Is that him, really? No, I think this is his son, maybe. Or just somebody talking about him. That's not him. This is him here. And French guy. And so Lie theory did begin with Lie, Sophus Lie, but Cartan is perhaps the greatest mathematician of the 20th century, perhaps. But he looked at the work from Sophus Lie and others, including Wilhelm Killing, and he kind of, brought together Lie theory in the most comprehensive and sort of complete way at the time. So he's got a lot of different contributions. And so, it took Einstein about 10 years to come up with general relativity after he realized that there was some kind of problem that needed fixing. And for a while, he had stuff that had to do with twisting and is it somewhere in here? This teleparallelism. So it says, let me make this bigger. So, yeah, so this is about Einstein-Cartan theory. Think of it as an alternative to general relativity. Well, maybe I should read some of this stuff first. So one main reason why the Einstein-Cartan-Kibble-Schema theory is so unpopular even today is its extreme mathematical complexity. The connection isn't symmetric anymore. So this is a thing with, I think, with general relativity, is that the connection is symmetric. Yeah, I'm not going to explain exactly what that means right now, but so it changes a lot of things in the mathematical formalism. For example, the covariant derivative applied to a simple scalar field doesn't commute anymore. So you have this thing called torsion. I realize this is probably pretty small. Torsion field. So it's really, there's more to do with twisting, basically. So pros, it's a natural extension of general relativity. GR feels more complete with spacetime torsion. Cons, it's terribly more complicated than GR without torsion. Torsion occurs only inside matter in cases of extreme high density states, so it's very hard to test it in the labs. Propagating torsion outside matter is probably too weak to be observable at all. Yeah, comment number 2 here. The theory is actually viable and very interesting in its own right. Yeah, it's kind of stuff I already said. This answer is quite long. But let's see. When Einstein worked on his theory of gravity, the notion of a connection was, at least to most, still synonymous to that of a symmetric connection, i.e. in particular. So when I think of a connection, I'll briefly mention sort of an intuitive way of thinking of what that's about. Basically, you have a manifold, which is a sort of the mathematician's idea of the generalization of a surface, basically. So you have so a circle is a manifold, but a manifold has a concept of a distance attached to it. So there's topological spaces are these things where you can imagine stretching them. So if you talk about like a torus, which is like a donut shape, you can talk about it as a topological space, and what defines it is that there is a hole as opposed to, say, a sphere. And mathematicians sort of talk about this in a way where you're allowed to stretch it. And that's how topology is normally done. But if you attach what we call a metric, which is a way of measuring distance, onto the every point on the surface, then you can't go around stretching it anymore because you would change the metric. And so then that's how you create a manifold. So it's just a generalization of this idea of a surface. And so you can kind of define the manifold by saying that at every point on the manifold you have I guess it's called a tangent bundle. You have a vector space, basically, that is tangent on the surface. So, for example, imagine a sphere. As you walk along the sphere, like the Earth, for example, you have, for example, longitude and latitude. You can imagine two vectors shooting out your tangent vectors, right? Like if you're walking on the surface of the Earth and you're walking straight, you can imagine a tangent vector sticking out in front of you. So imagine maybe a sphere that is a bit smaller than the Earth. So you have this tangent vector sticking out, and then the tangent space there is two-dimensional. Because we're in 3 dimensions. So if you imagine yourself as the origin, there's a 3-dimensional vector space. But if you take only the vectors that are tangent to the surface of the sphere, that is a 2-dimensional vector space, a subspace of the 3-dimensional space. So this is kind of the image that we're working with. Now, a connection is this thing that tells you when you go from one point to the next, how this tangent vector space changes as you move along. So connections are used in this study in differential geometry and all this stuff as part of describing curvature, that kind of stuff. So that's roughly what a connection is. And so yeah, the notion of so at this time, this is like between 1905 and 1915. Is that right? I think that's right. Yeah. Or is it 1915 to 1925? I forget. Anyway, when Einstein was working on general relativity, the notion of a connection was to most symmetric. And so if you imagine on the surface of a sphere, this is just me kind of spitballing, but if you imagine you have like a quaternion field, on every point you have a quaternion, you can imagine that you sort of define an amount of twisting at every point on the sphere. I don't know, that kind of thing is interesting to me. So I think I need to look into connections that are not symmetric. So he was later approached by Einstein-Cartan, and in fact there's this, I found on Amazon, there was, where is it? Here. There's a book, Einstein-Cartan and Albert Einstein, Letters on Absolute Parallelism. So I guess they exchanged a bunch of letters. It's got the original German and French together with the English translation. So I may put Amazon links that may be affiliate links. I'll just say they're affiliate links. I don't know if they will be actually, but okay. Anyway, I might get this. I don't have it, but it sounds interesting. Einstein-Cartan has become my favorite mathematician now. So I've been reading a lot of his stuff in French, and it's just fantastic to read. His style of writing is really great. Okay, yeah, I'm not going to go too much deeper on this page. At the time, the concept of intrinsic spin as used in contemporary quantum field theory was not yet prominent. So there's this other book. Actually, let's look. When you just search Cartan, unfortunately, you get... Let's see. Does it say... It's saying delivered to Japan. So maybe if I change... I don't want to type... Here, I'll type in... What's a zip code? Random zip code in America. It's saying generate zip codes? Whatever. This'll do. Okay, I don't think it changed. Anyway, yeah, it's unfortunate that you don't, like, the first stuff you get is curtains. There's also this book. This book is available in PDF, but it seems like it could be interesting. So I think Cartan was one of the first to really properly develop the idea of spinors, which kind of makes sense because it's related with Lie theory, Lie groups and all that. So where was I? Okay. Not sure how much of this I should read through here. Baffling success and novelty of GR stands second to few. It has some obvious flaws. Huh. So there's a lot of stuff I want to dig into. There's an additional tensor field, the torsion. But the beauty of Einstein-Cartan theory lies in the lack of exotic additions to the action, both mathematically and in overall form. The action remains an integral over the curvature, which now can be split into the usual curvature of the Levi-Civita connection and contributions due to non-zero torsion. Okay, so cons... sounds like what the other person was saying, that it's going to be hard to... if this stuff is true, so if this is the correct version of gravity, then... and it might be important for unification, then it sounds like it's going to be hard to expose it in experimentation. Torsion has an algebraic and linear differential equation and thus vanishes completely in vacuum. While this is also true for the Ricci curvature, that's something from general relativity, this does not imply that the Riemann curvature tensor vanishes. Okay. So prose. EC seems to give simple answers to several problems of cosmology without exotic matter, inflation field, or singularities. EC can be normally formulated as a gauge theory of the Poincare group. Poincare group is where you take... So before that, you start with the Lorentz group, which is the rotations in special relativity. And then when you add translations, you get the Poincare group. Torsion is a part of gravity already. There exists... So this is with EC, of course. There exists an equivalent formulation of GR using a connection without curvature but non-vanishing torsion. It is called teleparallel gravity and was pioneered by Einstein himself when he tried to unite GR and Maxwell's theory of electromagnetism. In this theory, torsion takes the role of a force in a flat geometry, providing the same evolution as GR. So intrinsic spin has no analog in classical GR. This is addressed in EC via this natural spin torsion coupling that provides many interesting effects at high densities. Okay. Also provides a natural derivation of the conservation of total spin. All in all, this makes EC a promising candidate for advances towards the theory of quantum gravity. Yeah, this is why I'm interested. There exist many approaches to solve even further problems of contemporary physics using EC and extensions thereof, including dark matter, black hole information paradox. Okay. This is an active field. Okay, conclusion. Interesting and natural extension of Einstein's gravity that certainly deserves more attention than it has gotten over the majority of the past century. While many of the answers it proposes for long-standing questions of physics sound promising, they remain partly elusive in the face of current experimental possibilities. It will likely be the touchstones of quantum gravity and cosmology that ultimately decide if this is realized in nature. Okay. Okay, cool. So it's kind of a general overview of this thing. And yeah. Okay, cool. This parallel, yeah, so this is what Albert Einstein was working on, I guess. Which I will study a bit of this. Okie dokie. So I found... First I found this one. It seems very interesting. Lectures with this woman, Ruth Gregory. And so this seems very interesting, but I decided to go back to the first lecture, which is right here, and watch through it a bit. It's a bit tough, and so on the second one, she gets into Lie derivatives and symmetries. This stuff is really interesting because Lie theory stuff is all over particle physics, but up until now, I've never seen it talked about in the context of gravity, I don't think. So, yeah. Now, unfortunately, these videos are in like 360p, and it's sometimes hard to make out what she's writing on the board. And it's also quite difficult. So I have been looking at this playlist, or I plan to go through this playlist that, for example, there's this exterior derivative thing that is sort of complicated. So, but that's kind of basically what we're talking about here. We're talking about differential geometry. So if I want to understand this Cartan-Einstein theory, I need to learn this stuff, basically. Okay, I was going to talk about also this book, which I'm going through, and it's, so it says, Differential Geometry, Cartan's Generalization of Klein's Erlangen Program. And so Klein's Erlangen Program, so Klein you may have heard of like Klein bottles and that kind of thing, but Klein had this idea to describe other geometries. So there's these other geometries that aren't just Euclidean geometry. And so Klein had the idea to describe them using group theory. That basically, group theory can describe the symmetries in the geometry. And so that was his idea, was let's describe these sort of more exotic geometries via group theory. And so Cartan did some work on this and so before Cartan worked on it, Riemannian geometry was sort of off separate from this Klein geometry, and Cartan sort of brings them together and sort of generalizes this whole thing. So that's why it's called Cartan's generalization of Klein's Erlangen program. And honestly, it's pretty tough. And I'll just read a little bit from the preface here. Let me, if I can find it. I should have earmarked it, but let's see. Yeah. So this is the author speaking, or I'm just reading what they wrote. So an author often writes a book in order to sort out his or her own understanding of the subject. This is the circumstance in the present case. When I was an undergraduate, differential geometry appeared to me to be a study of curvatures of curves and surfaces in R3. As a graduate student, I learned that it is the study of a connection on a principal bundle. I wondered what had become of the curves and surfaces, and I studied topology instead. So they're saying that this book is part of them sorting out their own understanding on the subject. So that's why it's kind of hard. It's a high-level book. And there's a foreword in here by Chern. Chern is a famous Chinese-American mathematician. Chern worked together a bit with, I think is it pronounced Simmons? And this guy is the founder of Renaissance Technologies. It's a famous hedge fund. I think this guy Weinstein... No, I'm mixing this up. Anyway, it's a famous hedge fund and a very famous guy, and Chern is a famous mathematician. He wrote the foreword in this book, and but unfortunately I don't even understand the foreword. But he says, in his preface, so he says, I'm honored by Professor Sharp's request to write a foreword to his beautiful book. In his preface, he asks the innocent question, quote, why is differential geometry the study of a connection on a principal bundle? Unquote. The answer is, of course, very simple. Because Euclidean geometry studies a connection on a principal bundle, and all geometries are in a sense generalizations of Euclidean geometry. And then it goes on to understand the math, which I don't understand. So anyway, this book, I'm reading a bit of it each day. This one, and it's pretty heavy duty. But it's good to not, like, it's not enough just to watch lectures and read papers. You probably need some textbooks. So, also there's this thing, so there's the complete works of Einstein-Cartan, and so it looks like this. Now I was looking for a PDF of this, but this looks like it's not that big, but this is like probably 4,000 pages. This is at least 3,000 pages. These are huge books. You just can't see the scale here, but yeah, they're huge. And I'm in Japan, and I really wanted to look at these books. So my wife looked for me and found that there are, I think it was 37 libraries in Japan that have this book. They're probably all university libraries, I'm guessing. But anyway, we went there to one of them. But I just thought, this guy's my new favorite. Well, of course, most of this is in French. Some of it's in German, but 98% of it is in French. So you can only really read it if you know French. But anyway, it's super enjoyable reading, to be honest. And he's kind of my new favorite mathematician. And I think if I spend a lot of time reading his work, it's really going to propel me forward, both understanding Lie theory and all of this stuff, differential geometry stuff I've talked about today. And definitely this Einstein-Cartan theory version of general relativity is definitely of interest. But yeah, so I think for me this is going to be my way of like choosing a library that if it has these in it, then it's worth going to. So I can, whatever country I'm in, I can ask around and figure out if I want to go to a library, I can find out, first of all, does it have this? And we're talking about, the one we went to is a university library, so it's a huge, it's like 6 stories, which, of course, there's much bigger libraries out there, but it's going to be my litmus test for if it's a library that I want to spend a lot of time in, basically. And walking around the math section in a university library is kind of interesting. So Einstein-Cartan has a son named Henri-Cartan. I'm guessing he may have named his son after Poincaré, Henri Poincaré, maybe. And I suspected that Cartan knew German because he was influenced by Wilhelm Killing's work, and that was confirmed looking at this because some of the stuff he wrote was in German. So I kind of want to learn German, but that will take some time. Anyway, this is the stuff that I'm studying, and differential forms. I might buy a couple more books. Cartan for beginners. Yeah, but I think it might be the most important 20th century mathematician, and he's not talked about as much as he should be because it's kind of high level. It's Lie theory stuff, differential geometry. I think most math majors maybe do study some differential geometry. I'm not sure if most of them do or not. But it's sort of graduate level, I guess. So you don't see a lot of people talking about it. But I mean, spinors, Lie theory, that stuff is super interesting. So anyway, I'll leave it at that. That's a good place to stop. Adios.